Okay, so today we're going to be talking about the group 15 elements. So some of the basic trends that we see are that the ionization energy increases as you go down the column, with nitrogen having the highest and bismuth with the lowest. The electron affinity generally decreases as you go down, with the exception of antimony having a higher electron affinity than bismuth. We see that they start to behave more metallically as you go down. So nitrogen and phosphorus are non-metallic, and bismuth behaves metallically. The electronegativity is slightly variable, but decreases in general as you go down. Nitrogen does have the highest, and antimony has the lowest. And we see that the reactivity also increases as you go down the column.
Okay, so there are some important reactions regarding nitrogen specifically. For one, is the Fritz-Haber reaction. Inert nitrogen gas is normally not supposed to be reactive with many elements, but they were able to figure out a way to use nitrogen gas combined with hydrogen gas in order to produce ammonia. Secondly is the oxidation of hydrazine. Hydrazine is a very common reducing agent, and they're able to produce things such as nitrogen gas with that, and ammonia as well, with the like a metal catalyst, which hydrazine is reactive, very reactive with metal ions. And then third, the synthesis of nitric acid. This is a three-step reaction that ends up with the HNO3, which is nitric acid. And nitric acid is important for synthesizing ammonium nitrate, which is commonly used in things such as fertilizers and explosives like TNT. So some other important reactions with the other atoms on the group 15, the synthesis of phosphoric acid using calcium phosphate and sulfuric acid are able to synthesize phosphoric acid. And then the synthesis of ammonium trioxide using ammonium sulfide. Ammonium trioxide is a white powdery sand-like substance, and is often used as a flame-proofing agent.
So nitrogen forms bonds with a lot of other molecules. The main one is that they form bonds with a lot of the halogens, as we see in the bottom right-hand corner with phosphorus and chlorine. So nitrogen also forms nitrous oxides and oxyions when bonded to oxygen. It can form ionic bonds as a nitride or as an azide with group 1 and group 2 elements. And the other elements from group 15 can form metallic bonds with group 1 and group 2 elements such as lithium or magnesium.
And then a lot of nitrogen or group 15 compounds and the elements themselves have a lot of life applications. Hydrazine, as talked before, is used as rocket fuel, especially because it doesn't produce CO2 in the combustion of it. Arsenic is used to alloy lead and is typically used for N-type doping in semiconductors, specifically in stuff like LED lights. Nitrogen is a key element in nucleic acids of RNA and DNA. Ammonia is key in producing commercial fertilizers. That's the huge importance of the Haber reaction. Phosphorus is also used in fertilizer production. It's also used in LEDs. It's used in safety matches and flares that like red tip at the top of safety matches, typically some phosphoric compound. Antimony is commonly alloyed with lead for lead acid batteries and used as a flame protecting agent. And bismuth is used in cosmetics and a variety of medicine. Specifically, most people know Pepto-Bismol. And then some interesting facts about these elements is nitrogen is often used with quantum dot doping, or as used in quantum graphene quantum dot doping, which is in the top picture is a graphene quantum dot. And is used to tune the intrinsic properties of these quantum dots, specifically their electronic characteristics, and probably the most important thing is their optical activity. Phosphorine, which is like a sheet of phosphorus, kind of like graphene, has or shows semiconductor characteristics and is promising candidate for use in flexible nanosystems, specifically a lot of flexible, really small electronics. And then phosphorine, arsenine, layered antimony, and layered bismuth oxyhalide nanomaterials are studies in the mean of drug delivery for cancer therapy because they break down pretty easily and they're fairly non-toxic, especially phosphorine. That's it.